Let's turn to cheese. A storage serendipity. So I'm getting back to this idea that the use of animal products led to some important discoveries and so the emergence of some very important foods. Cheese was discovered, I say serendipitously, because milk was probably stored in animal tissues, the sacs that are naturally available when we dissect an animal. Why? Well, we'll talk about, and I think we've already mentioned the idea that an enzyme present in rennet, which is an extract of calf stomach, is responsible for the coagulation of milk proteins. So rennet, what is rennet? Well, it's a natural component of the calf abomasum, which is just Latin for before the intestine. And here it is, the fourth stomach of the cow, as you see right before we enter the intestinal tract. The calf abomasum is particularly rich in an enzyme called renin, as we'll see, and this enzyme alters the structure of milk proteins, allowing them to precipitate. And it makes perfect sense that an animal, a calf, that whose main source of nutrition is its mother's milk, will have a specific set of enzymes designed to degrade, break apart, destroy, digest the molecules presented to it by its mother's milk. An important idea that we'll come back to is that rennets are milk specific. So the enzymes that are present in any given organism will be specific to the kinds of milk proteins that are generally presented. So calf rennet is specific to cow milk proteins. We'll come back to that. So again, the serendipity, right, and I say serendipity because it was accidental and wonderful, is that cheese was probably discovered when the ruminant milk was stored in those stomachs because it was a convenient, you've already killed the animal, you suddenly have a very, Ziploc bags didn't exist, plastic grocery bags didn't exist, so you have a very resilient and convenient storage system in the various tissues of the animal itself. So when we happen to store our milk in the abomasum, shake it around, let it sit for a little while, suddenly cheese. What is rennet? So rennet is a complicated mixture that's extracted from calf stomach. It contains an active ingredient called renin. The more scientific name for renin is chymosin. This is a molecular structure of chymosin, and at the beginning of the semester, I showed you some of these complicated structural diagrams of proteins. This is an enzyme. It's a very large molecule. The structure is very complex. Let's suffice it to say that chymosin is a protein. It is an enzyme. It is a protease. That is to say, it's a chemical catalyst that does a specific job, and that is chop up proteins. That's what protease means. For those of us that are biochemists in the audience, it's an aspartyl protease. So you see that there are two aspartic acid amino acid side chains there. They play the key role in chopping up the cow milk proteins. Now, what is a protease? So here's a peptide bond. We've seen peptide bonds before in this class. What happens with a protease is that peptide bond is chopped right in half, and we're left with two segments of protein. So we'll come back to that. But what I'll say again is that renins or rennets or chymosins are very specific to the organisms that they are derived from. Well, you might imagine then that given this idea that the rennet is something that's derived from the calf, this might upset you if you're a vegetarian, a strict vegetarian. You love your cheese, but you certainly don't want to use animal products. Rennet is definitely would have to be considered an animal product. Happily, there are a lot of vegetable and microbe-derived relatives of renin available, and those are frequently used in cheese making. However, the most commonly used rennet currently in use in the cheese making industry is calf rennet, but it is genetically, you'd have to consider it a genetically modified or a recombinant version of the calf enzyme. So that is to say, we take the gene from the cow for chymosin, we put it in a bacterium and use the bacterium as our mode of expression. So we use the bacterium to generate our chymosin, and then we purify that away from the bacteria and use that in our cheese production. So we're pretty far away from the cow at that point, but then you have a new issue to worry about. That is to say, what do you think about use of recombinant proteins, genetically modified organisms in your food? We'll talk about that issue more as the semester goes along, but it's an interesting one to think about, these conflicts. In any case, if you want to stay away from calf rennet altogether, you can certainly do so using these others. I will say, however, that because those enzymes are all more or less specific to the organisms that they're derived from, they can result in some subtle differences in the cheeses that are produced with them. If you use vegetable or microbe rennet instead of cow rennet in your cheese, you might expect to get some different flavors or textures or other qualities. Back to what rennet does. So on the left here, we see a picture of milk. We have fat globules and we have these hairy casein micelles, which we talked about extensively in the last lecture, and they're all nicely suspended and not really interacting with each other too much. And that's because the casein micelle, remember, it's a complex of 3 different caseins, is covered with hydrophilic, negatively charged molecules of kappa casein, and they effectively prevent the caseins from interacting with each other, so they stay dispersed. Well, what rennet does is cleave off the end of that kappa casein, releasing that hydrophilic peptide, making the casein micelle itself more hydrophobic and more prone to aggregation. And what we see then is the formation of these long, extended networks of aggregated aggregated casein micelles. Now this is I want to distinguish between protein denaturation, where the casein micelle might be completely disrupted and would form a different kind of network. In this case, the casein micelle is more or less still intact. In any case, those micelles arrange to form this long-range and very firm network, and that's what gives us the curd. Right. You can also curdle milk with acid, and that's an important part of most cheese making. But you can skip the rennet entirely and just use acid, and that's because as we lower the pH, we also mask some of the charge on the chymosin micelles themselves, and it's those negative charges, in part, that keep those hairy casein micelles from interacting with one another. So once we screen those charges, the casein molecules all start lining up, binding together, and forming this network. Acid curdled milk minus the rennet will form more brittle curds, but usually we do both of these are done. So no cheese, for the most part, without some rennet. Let's talk about cheese bacteria and the molds that are important in cheese making. These do a lot of wonderful things for us, but mostly what they do is degrade the fat and protein that are present in milk, generating lots of other molecules that have great flavor or great texture, or otherwise change the characteristics of the food. Starter bacteria are used, and we'll distinguish these from the molds that are used to help age cheeses. The starter bacteria, as we've already seen, tend to acidify the solution. We've talked about the value of that in terms of helping the casein molecules begin to aggregate. We also ferment our sugars down to lactic acid. That's important, as we've talked about. Again, that's that acidification again. But they also help, again, develop the flavor during the ripening. We've talked about most of these bacteria already. Lactococci, Streptococcus. These are bacteria that are present in many of the cheeses. Some of them have other interesting characteristics, like tolerance to high temperature changes the way that we can treat the cheese as we're preparing it. Maybe we can cook our cheese at elevated temperature for a variety of reasons. Maybe we want to drive off water. Maybe we want to promote certain kinds of chemical reactions that are going to happen more frequently at high temperature. Another really interesting bacterium that's worth mentioning is the Propionibacteria. This is a bacterium that's found in Swiss cheese, and the great thing that it does, among other things, is generate carbon dioxide gas as it goes about fermenting milk components. And what this gas does is collect in pockets and this gives us the eyes of the cheese that we discovered last week in our interview with the cheese folks. So we get interesting textures and characteristics, holes in the cheese. We also get interesting byproducts of these reactions. Diacetyl, this is the molecule of diacetyl, gives us a very interesting aroma in many cheeses. Let's mention a couple of other bacteria as well as molds as we move forward. So smear bacteria, they're a family of bacteria, the Brevibacteria, that are frequently populate the rinds of cheeses. They we learned last week that most cheeses ripen from the outside in, so we'll coat the rind of the cheese with the bacterium, and they'll slowly penetrate. And even the bacteria, however, will die as the cheese ages, but the enzymes of the bacteria live on and continue to degrade some of the milk components. We get these sulfurous compounds formed by these bacteria, and these give rise to the familiar odor characteristics of, for example, Limburger cheese. And we remember that we learned too that a Limburger is a washed rind cheese, so we can look closely at this piece of Limburger and we'll see that it has a nice clean rind, at least visually, but that once washed, that rind becomes infested with these smear bacteria. I really want to focus for a few minutes on the molds, and we'll come back to the molds in cheeses. Penicillium molds are very important for the maturation of many, many wonderful cheeses. These molds are believed to degrade milk fats, which are typically long-chain triglycerides, to short-chain fatty acids, and these give rise to various interesting flavor traits like peppery flavors or spicy flavors, as well. These long-chain fatty acids get degraded to methyl ketones. Here's a structure of a methyl ketone. These also give us some of the recognizable traits of cheeses like Stilton and Gorgonzola, Roquefort as well. Yes, so some of those, the names of those organisms, Penicillium roqueforti. We of course know what kind of cheese that's made. These are molds that are natively present in the places where these cheeses are prepared. Although frequently now they're actually inoculated in the cheese itself. Certainly originally the molds were present as a happy accident. Once again, a serendipity leading to something that's really wonderful. Some different penicillins frequently used in the preparation of the Stiltons and the Gorgonzola, but it's worth noting that when I run down these very well-defined lists of bacteria and molds that are present in cheeses, to remember that what we're really talking about is something that can be very much more complicated. Many different kinds of bacteria present in a given cheese, many different kinds of mold, as well as yeasts also play an important role in cheese maturation and aging and ripening. We've also seen some examples of the white molds, again of Penicillium, but a white Penicillium camemberti, what cheese might this be important in the formation of? And most of the flavors that we see in these white bloomy rind cheeses are going to be due to protein degradation. So there's a camembert, for example. Again, remembering that the molds live on the exterior, and so what we see is the ripening of the cheese from the outside in. We saw examples last week of white mold ripened cheeses that are pretty unripe in the center, but nice and ripe at the edges. And that, again, is an interesting and wonderful trait.